Okay, so welcome to your new semester. I recognize most of you, but not all of you. My name is, if I can write it down. Okay, I'm Altu Özpineci. My office is right over there. I will not be putting any official office hours, so the basic idea is just drop by my office. If you can find me in my office, that means I'm free to discuss with you whenever you have questions. If I'm not free, I will just let you know. And today we will be, this semester we will be discussing starting quantum mechanics. I'm using this OptiClass system. I'm assuming you are all familiar with this. All the material will be put over there. I'm registering the courses. I'm making a screen capture. They will appear on that YouTube list. And the book we will be using will be the book by Sakurai, The Modern Quantum Physics. And if you want detailed information, you can just click on the link. It opens an Amazon page. You can find the details about it. I'm not saying you should buy from Amazon, but just if you get some copy of the book, it will be useful for you. Now, what we will be covering is, well, let's say, ideally, we should be covering the first 5 chapters of the book. So we start from this week, we will be discussing with the fundamental basic concepts and like what is the Hilbert space, what are operators, what are states, what are the bras and kets that we are using. Then we will be discussing the Schrödinger equation, Schrödinger picture, Heisenberg picture, and some simple systems like the wave equation, like the harmonic oscillator. And we will be, okay, then there is this chapter on propagators, Feynman path integrals, the gauge transformations. Well, we will need to describe how the particles interact with electromagnetic fields. So there we will need this discussion on gauge transformations because electromagnetic theory is basically a gauge theory. Have you ever taken electromagnetics course? Well, you should probably be familiar from undergraduate at least. The potential and the scalar potential and vector potential in electromagnetic theory is not gauge invariant, is not unique. There are infinitely many potentials that you can use to describe a given electric and magnetic field. Somehow this symmetry, let's say, if you change your potentials, electric and magnetic fields do not change. This is what we call the symmetry. It also reflects in the properties of the Schrödinger equation and the interaction of our Schrödinger equation describing the interaction of our particles with the potential. Because in the Schrödinger picture, the basic, the ingredients will be the potentials, like the scalar potential and the vector potential, but we know that they are not unique. So if we change the scalar and vector potential in the Schrödinger equation also, nothing should change. So that's basically what we mean by gauge symmetry. And then there's the chapter on rotations, angular momentum, addition of angular momentum, etc. Well, this is probably the most difficult chapter of this book. I mean, even many years from now, we will have problems with angular momentum, that I can guarantee you. I still have problems with angular momentum, to be honest. So it's one of the most difficult topics in quantum physics, let's say. And then we have the symmetries, and we close the semester with perturbation theory. Well, we will be sticking with time-independent perturbation theory. Time-dependent perturbation theory will be left for the next semester. Well, this is ideally what we should cover. Well, to be honest, I don't find it so realistic that we will be able to cover all of this. We don't need to cover all of this. The most important thing is that you should learn the material. I mean, well, I can cover the material, there's no problem with that, but if you are not following me, if you are not understanding what we are discussing, it just doesn't make sense. Okay, so because of that, I want your feedback. If you are going too far, just let me know, or if you are going too slow, again, let me know, because most of you have different backgrounds, you are coming from different universities. had this quantum physics, quantum mechanics course at different levels in your undergraduate studies. We will start from the basics, but just try to go a bit more deeper than what you had done in your undergraduate studies. So I'm assuming that even if you don't have a strong background in undergraduate, you should be able to follow this course. And if you have any trouble, just ask in the class. Now, most of the time what happens, even in other courses that I'm teaching, is that I just look at the faces of the students and I can tell that 80% of the students are not following. And then I ask them why they don't ask questions, and they say that they think that all the other students were following, they didn't want to disturb the other students. It never happens. I mean, so if you are not following, it practically means that the majority of the classroom is not following. One of you should be, at least one of you should have the courage to ask a question so that your friends will also benefit. Okay, so the exams and the midterms, etc. We will have 2 midterms, 1 final, and you will have homework. Well, ideally, I'm hoping to give 1 homework every week, more or less. Well, it takes time, so sometimes I cannot find time to prepare the homework. So I just fail to prepare the homework every week. But I will be aiming at giving around 1 homework every week. Not this week, not in the week of the midterms. So you will get around 10 homeworks. And the weights of these in your grade will be, each midterm will be 25%, final will be 25%, homework will be 25%. Well, sometimes I also consider just removing one of the midterms, just 1 midterm, 1 final, and the homework, and increasing the weight of the homework. But for the time being, these will be the weights. Yes, any questions? How many of you are from this department? Okay, half. No. Undergraduate. Undergraduate. Okay, so half and half, more or less. Okay, great. And anything else? Oh, the midterm dates. First midterm, April 1st, second midterm, May 6th. These are both Saturdays. Well, they usually start at 13:30, let's say 3 hours. Not because the questions will take you 3 hours, but I just don't want you to have worries about the time. I mean, you should have time to think over the problems and solve them. And at the end of the 3 hours, if you are still solving a problem, I just let you continue. And I'm not grabbing the papers from you. Now, these are just, let's say preliminary dates. When those dates approach, if you want to shift them, if it overlaps with some other exam, some other thing, we can modify the date. They're not hard-coded, let's say. But if you don't object to these dates, these will be the dates that I will inform the department about. And there's also one more final. After the final, there's a makeup. That will be the Monday after the finals. Well, it happens that in one of the exams, it's not just your day. you get a low grade, but in your other exams you get higher grades. So the general criteria I use for the makeup is if the lowest your two lowest exam grades differ by, let's say, 15 points, then you can take the makeup. If your exam grades, they just differ by, let's say, 10 points, well, it might be low for your expectations, but nevertheless, that's your level. If it happens that one of your exam is 20, the others are, let's say, 60 and 80, well, 20 is not your level. Something happened that day, it was not your day, so you got a low grade, so that's what the makeup is for. Of course, if you just have a medical report, you are still entitled to the makeup. Or if you don't feel like entering one of the midterms, you skip that midterm, that will count as 0. So if you take, let's say, at least 20 from the other midterms, you are still entitled to the makeup. And I'm hoping that you will be asking more questions during the lectures. Well, I mean, I have 2 more lectures right after this lecture, so we cannot combine it with these 2 hours. If you ask for it, I mean, we might try to find some other date, 3 hours, that will fit all of you. I'm not so fond of 3-hour lectures, to be honest, because most of the time what happens is at the end of the 3rd hour, you are all sleeping. I mean, you get tired. I mean, this course is supposed to be an intensive course, at least mentally it should be intensive. And 3 hours of intensive listening, no, I mean. So what my intention is basically to use 1 hour, this Wednesday hour, and also the first hour of the Monday lecture. Well, not the first week, but in the future weeks, at least let's say the first hours to be discussing new topics, if possible, and then use the second hour to solve some examples. I will also ask you to leave the the hour after the Wednesday lecture free if possible. I mean, okay, this course is a 3-hour course. This is the first time that I'm lecturing this course, so I don't really know how much time each topic will take. So what I hear from the previous lecturers is that they all claim that 3 hours is not enough. So if that is the case, I might start using the second hour after the Wednesday lecture. Or it might happen that from time, maybe not every week, but from time to time, we might be using that second hour, the hour after our Wednesday lecture, for solving more examples, discussing more examples. So any objections about the lecture hours? It shouldn't be overlapping with any of your other courses, any of the other graduate courses at least. Okay, so the hours, we are not changing them. And all these notes, I will also upload it in Otto class. And I also don't know your names, so may I learn your names? Well, learn, that's too much of a claim, just at least hear it once. İsmail. Bilge. Alper. Kıvanç. Merve. Altu. Ali İbrahim. Kaan. Hüseyin. Okay, so I'm hoping to learn them soon. Okay, so let's start with quantum mechanics. Well, I will be closely following your book, so it will be beneficial for you if you just get a copy of the book. And your book doesn't go through the historical development of quantum mechanics. Rather, it starts with the Bryant-Ket notation developed by Dirac. I mean, it has its advantages, so at least when we are discussing quantum mechanics, we will be discussing what we know about quantum mechanics now, rather than just going over all the wrong path that in the development of quantum mechanics we took. But we are also losing the information that, the current formulation of quantum mechanics is not what people came out with straight away. I mean, they tried many things, they made many failing attempts, and eventually we reached at this point. So there are many observational facts. We had this classical mechanics, and we had many observations just didn't match with classical mechanics. We couldn't explain them using classical mechanics. And one of them was the Stern-Gerlach experiment. Well, I had brought the, you can find the papers online. The paper by Stern and Gerlach is available online, and through Metu you can just read those. Well, they are in German, unfortunately. So if you speak German, you can even read them. The papers are from 1922, what they did in experiment and their actual observation. Now, what they did was they took a magnetic field. They created some non-uniform magnetic field. They say this is more or less the shape. There is a tip over here. And if you remember from your electromagnetic courses, if you put a magnetic dipole in a magnetic field, the potential is just minus mu dot B. Mu being the magnetic dipole, B being the magnetic field. So if you calculate the force would be just minus the gradient of U, which is the gradient of mu dot B. Well, for, let's say the Z component of the force will be just mu. That'll be, well, it will be, well, if mu is constant, let's say this will be F, the I component of the force will be just mu I, mu J, del B I by del X, del B J by del X I. Fi will be just, or we can also write it as mu J del Bi by del Xj. So the Z component will be mu J del Bz by del Xj, etc. Yeah, I mean, you can look at any components, just change its form, etc. So the basic idea is that this, okay, the force is proportional to the gradient of B, so that's why they created a non-uniform magnetic field. Now the idea of putting this tip is that very close to the tip, the gradient of the magnetic field will be very large. So it's just, I mean, it's a very cornered object, so the derivative, it changes very fast, so it also reflects in the magnetic field. The magnetic field will be changing very fast close to the tip. So we have a very fast changing magnetic field, and hence the force acting on our dipoles will be large. So this was the idea. So there will be a force acting on it. Well, the gradient is mainly in the Z direction. So there will be a force along the Z direction. And if you send any magnetic dipole through it, they will just spread out depending on the angle between the magnetic dipole moment and the magnetic field. So how they create this object with magnetic dipole moments, well, they basically have an oven with an opening. This is our oven. So here is their apparatus. Inside the oven, they heat silver. They just pick up those that are moving in a given direction. There is a collimator over here. So they basically choose the silver atoms that are moving in the same direction. So to start with, they have a beam of silver atoms that are moving straight in one direction. So what they do, if you read the paper, at least from the figures, what I could understand was, without the magnetic field, there's a screen over here. Without the magnetic field, this is what they observe. There's no magnetic field, so the silver atoms, they just go straight. Well, they still have this spread, so they just make a thin, wide line. And then they turn on the magnetic field. So what you would expect is the force will be related with the angle between the magnetic field and the magnetic dipole moment. Well, in the oven, the silver atoms, they're just moving in random directions. They have random orientations. So that's also what you would expect from their magnetic dipole moments. Their magnetic dipole moments should also be randomly oriented. So there will be a spectrum of angles. And depending on the angle between the magnetic field and the magnetic dipole moment, some of them would deflect from their original path very slightly. Some of them will be deflected largely with a large angle. So you would still get another spectrum. Your expectation would be to get something of this shape. So some of them will still go straight. They will make 90 degrees with the magnetic field. Some of them will make almost 90 degrees, but not exactly 90 degrees. They will be deflected very slightly, etc. So each one of these points here, well, they will just spread out. So that is what one would have expected classically. But this didn't match the observation. So this was without the magnetic field. The observation was this. I will probably bring the paper in the break. So it's just, they still have kind of a thickness. So this is what was observed. They either deflect in one direction or deflected in the other direction. There were none of the silver atoms were deflected in intermediate angles. So here, this region is empty. None of them went there. Well, the interesting thing about the silver atoms is that you see, it has 47 electrons. Now, 46 of them, they just make, well, now we know that they make this perfectly spherical electronic shells. So their net spin is 0. So their net total magnetic dipole moment is 0. But there is this additional electron. That gives the silver atom its spin. It should be in the 5s. Yeah, we will eventually study the hydrogen atom. So this additional silver atom, it doesn't have any angular momentum. It only has spin, and hence the silver atom has a spin, has a net spin. And now we know that it's a spin 1/2 object. The electrons at least have spin 1/2. But there is also the nuclear spin, but we will also see that since the nucleus is so heavy, it doesn't really influence much. So it's basically the electrons that interact more strongly with the magnetic field. The main reason is that the magnetic dipole moment of an electron just turns out to be E/mc s. This is the magnetic dipole moment of an electron. Well, you see the 1 over the mass. The electron is light compared to the protons and the neutrons in the nuclei. So even the protons and the neutrons, they would interact with the magnetic field. Their interaction will be, since their mass is 2,000 times heavier, the interaction of the nuclear spin with the magnetic field will be weaker by a factor of around 1,000 compared to the interaction of the electron. So it will be mainly the electron's magnetic dipole moment that will contribute to the interaction of the silver atom with the applied magnetic field. So that's why we only care about the electrons, and this single electron causes the silver atom to have spin 1, to have a total spin h⁻². And now we know that that is what causes this splitting. Now that is something we will be discussing eventually in detail in the spin, but currently just using the Stern-Gerlach experiment, the only thing we can say is that if you don't want to discuss about the spins, etc., these silver atoms are practically of two types. One type is deflected in one direction in the magnetic field, and there is also the other type that is deflected in the other direction in the magnetic field. And there are no silver atoms that will be deflected in intermediate directions. So that is basically what we now call a two-state system. So the silver atoms, there are basically two kinds. That's what we mean by two states. Now, of course, using the Stern-Gerlach experiment, we can separate these two different kinds of silver atoms, and that's where the fun starts to begin. So let's discuss some of the hypothetical experiments. We have a Stern-Gerlach, let's say we have a Stern-Gerlach experiment over here. Let's say it's in the Z direction. We are applying a magnetic field. So we are free to choose the direction of this magnetic field. And the direction of this Stern-Gerlach apparatus is in the Z direction. So it splits the silver atoms in the Z direction. So when we send a group of silver atoms in this Stern-Gerlach experiment, some of them go up, some of them are deflected down. So we can block some of them. So we said that, okay, these silver atoms, they just come in two varieties, one deflected up, one deflected down. So I can separate them. Basically, I'm making a spectrometer out of this Stern-Gerlach experiment. So I just split them up and pick up one of them. Okay, so this is my the type of silver atoms that are deflected in the plus Z direction, let's say. So this is plus, I will call that plus, this one minus. Well, I use another Stern-Gerlach experiment. Identical one, again in the Z direction. Now, without any surprise, I only have the up type. There is no down type. Well, basically, that's kind of expected because I already chose the type that is deflected in the upward direction.
Is this the experiment result or what we expect?
Well, I was looking if this experiment was actually done or not. I would be surprised if this experiment is not done. But I don't have the reference. If I find the reference, I will just post it in the class also. If you have just one Stern-Gerlach experiment, you can just add the other ones also. But for the time being, let's say this is what is expected, and this is what is observed. Now let's do some other experiments. Again, I have this Stern-Gerlach experiment in the z direction. Split it up and down. Again, I just block the lower one. And let's say now I put another Stern-Gerlach experiment with a magnetic field in the x direction. Why not? And what I would observe is that, again, it's split it into two. So let's say this is z plus, z minus, and we can just name them as x plus and x minus. Nice. Okay, still there is no surprise. So I can just say that, okay, this silver atoms over there, they are Z plus type and also X plus type. Okay, that is what I would just conclude from these two experiments to start with. It's Z plus and X plus. But if it is Z plus, then if I put it through another Stern-Gerlach experiment, they should only be deflected upward. Just like the first case. Because I'm already choosing the Z plus type. Okay, so let's do that experiment. Okay, the Z Stern-Gerlach. I have these two different types of silver atoms. I take the Z plus type, I send it through another Stern-Gerlach experiment in the X direction. Is X plus and X minus. I block, let's say, X minus. So I take the above one. I send it through Stern-Gerlach experiment, the first one. So if I could say that, okay, this X plus that I have chosen, I had already chosen them to be Z plus. Now it is also X plus. So what I have are silver atoms of the types Z plus and X plus. If I send it through another Stern-Gerlach experiment that will split it in the Z direction, well, that should be only Z plus. But that's not what experiment tells me. What it tells me is I get Z plus and also Z minus. I can also count them. So you see, if I have the Z plus silver atoms, if I send them through an X Stern-Gerlach experiment in the X direction, 50% goes above, 50% goes below. It's 50%, 50%. Well, you can say that, okay, in going through the X plus X Stern-Gerlach apparatus in the X direction, maybe something happened there. Some of the Z plus was somehow converted into Z minus. But it's not just some. It's just, again, 50%, 50%. So somehow, the Stern-Gerlach experiment in the X direction completely destroyed any information, any information about the previous Stern-Gerlach experiment. So you see, we started with a beam of silver atoms. We don't know anything about them. Then we send it through a Stern-Gerlach apparatus and chose the Z plus. So that now we already know that those are Z plus. If we measure the Z, if we send them through the Z Stern-Gerlach experiment again, they are still Z plus. Nothing goes through Z minus. But if we send them, we choose the Z plus and send it through X plus, through Stern-Gerlach apparatus in the X direction first before sending it to another Stern-Gerlach experiment in the Z plus direction, then our choice, our first choice of choosing the silver atoms of the Z plus type, that information is completely erased. So you see, what we get from this Stern-Gerlach experiment in the X direction is 50% Z plus, 50% Z minus. So that is where they say the quantum mechanical weirdness, they just start to show themselves up. Now the problem is, now we have this experimental observation. Okay, you see, in physics, and if you think about physics, what we do in physics is we first start with some observation. We make a mathematical model for that observation first. So classical mechanics is one kind of a model that we have to describe nature. Then we make manipulation with that mathematical description, mathematical representation, and eventually we represent what we get. So that is also something that we should do. So we started with one simple, this is our observation. Well, this experimental setups, they are already giving us some mathematical model for this system. So for example, if you start with this one, the first setup, we have a Sturm-Gerlach, we have a beam of silver atoms, we send them through a Sturm-Gerlach apparatus, they are split into two. So that is where we begin building our mathematical model. We say that, okay, the first beam is maybe 50% Z plus, 50% Z minus type. So that's the model. Then we send it through, let's say, the X hat. We take the Z plus and send it through the Sturm-Gerlach X hat apparatus. And then we can say that, okay, this Z hat silver atoms, let's label them, let's give them some names. They are also a mixture of 50% X hat silver atoms and 50% X minus silver atoms. Okay, that's still our model. But the problem is the third experiment tells us that our model, our understanding in terms of these probabilities or these mixtures of different kinds of silver atoms, it just doesn't agree with our observation. You see, we would have said, okay, the first Sturm-Gerlach apparatus, we chose the Z plus types. The second Sturm-Gerlach experiment, we chose the X plus type. So we have some, now our model is basically, we are giving labels to our silver atoms, they are X plus type, they are Z plus type, etc. And this third experiment tells us that, no, this doesn't work. Because if this would work, through the third Sturm-Gerlach apparatus, we shouldn't be getting any Z minus because we had already chosen the Z plus type silver atoms. So that choice we had already made. And then in addition, we chose the X plus type, but somehow this choice of X plus type had already destroyed its property in the Z directions, let's say. So we should develop some other model that can take this erasing of information into account. Even in classical mechanics, we have a similar system to this one. Are you familiar with anything just like this one from classical mechanics? Classical physics, let's say, not mechanics, but... No, that is quantum. Let's look at optics, classical optics, Maxwell's equations. Do you remember your optics courses? Polarizers. Do you know what polarizers are? Have you heard of them? I'm sure you have all used them. Do you know where you are using polarizers? What? Filtering what? Sunglasses. Sunglasses, okay, that's one thing. There, for example, you are basically using the, you are eliminating half of the unpolarized light. That is one advantage. You are using the Brewster angle, for example, used in some polarizers, especially if you have a polarizer sunglasses. You might look through a glass at a particular angle so that you would just see through without any reflection, if you adjust your angle properly. Where else are you using polarizers? And also 3D glasses. These are cheap, and you can just make experiments with that. 3D glasses basically use polarizer filters. You see those plastics are they just filter different polarizations. So let's see. I brought 3 of them, so we can now, in the break, we can do this experiment. So basically the idea is, let's say you have a polarizer, a polarizing filter, let's say in the Z direction. And then if you just add next to it, you put another polarizing filter, let's say in the X direction. You shine some light through the first one. It will be completely blocked in the second one. So essentially the first filter just chooses light with a given polarization. The second filter, since it chooses light in a perpendicular polarization, so there won't be anything passing through it. But let's do this experiment. So you have 2 of these. And in between, you put a third polarizer. Let's say X hat prime, some 45 degrees. They just go through. You see, it is as if the first filter just erases, eliminates the light that is polarized in the X direction. But the second filter, at 45 degrees, essentially kind of regenerates it, so that there is some light passing through the third filter. Well, just like over here. You see, this first Stern-Gerlach experiment with this blockage that we put over there, we are eliminating the Z- type silver atoms. And if we put another Stern-Gerlach experiment, we actually see that it's completely eliminated. There is no Z- type. But if we put some Stern-Gerlach experiment in some other direction, in between those 2, although we eliminate the Z- type, we can regenerate the Z- type through this setup, through this intermediate Stern-Gerlach experiment. Now the phenomena is exactly equivalent to this one, although this is a classical example. This is valid in classical electromagnetism. Do you know how it comes about? So let's see how we describe this.
By the way, would the Maxwell equations explain this?
Sure, no problem. Now we will explain it. You see, this perpendicular plane is the XZ plane. Okay, I would. Okay. So this perpendicular plane is the XZ plane. So the polarization, let's say the electric field after the first polarizer, the electric field in general, let's say, it will have this form. E0 times cosine K y minus omega t. Okay, it's moving in the y direction. And this E0 vector is a vector in the XZ plane. So it will have some E0x in the x hat direction plus E0y in the y hat direction. So this is our initial light, the polarization of the initial light, if it is polarized. Let's assume we just send some arbitrary polarized light. Now, after first filter, let's call it E1. It just chooses the polarization in the Z direction. It just absorbs all other polarizations. E1, I'm sorry, this is not Y, this is Z. So E1 is E0Z cosine ky minus omega t in the Z direction. Now, if we send it through a polarizer in the X direction, of course, there is no polarization in the X direction. X direction is perpendicular to Z, and so we are done. So there won't be any light passing through it. It will absorb all of it. But then if we put this 45-degree polarizer, well, let's give them some names. So this is my Z. This is my X. Let's say this is our X prime. This is our Z prime. And this angle is 45 degrees. So Z hat, it has a component in the X prime direction with a magnitude 1 over square root of 2. X hat, X prime hat, plus 1 over square root of 2 Z prime hat. This is our Z hat in terms of X prime hat and Z prime hat. So E1, I can write it as E0Z cosine ky minus omega t, 1 over square root of 2 X hat prime plus Z hat prime. So after the second filter, it just chooses the polarization in the X hat prime direction. So this is what we would have. This is after the second filter. Again, let's come back over here. X hat prime, you see, this is our X hat prime. X hat prime is nothing but 1 over square root of 2 X hat plus 1 over square root of 2 Z hat. You see, now we have an X hat component. You see, we start with an arbitrary polarization. We send it through a polarizer which is aligned in the Z direction. So after the first polarizer, we have a light that is only polarized in the Z hat direction. Then we put this intermediate filter at 45 degrees. After this filter, we again have some light polarized in the X hat direction. So it is kind of regenerated due to this intermediate polarizer. So I'm not saying that this is what happens also in the Sturm-Gerlach experiment. But what I'm saying is that we already have a mathematical framework which describes these observations in a different physical system. So what I will be doing is basically borrowing that mathematical framework to describe this system. Because we had already, our first guess was, okay, let's just give these silver atoms some labels. But it didn't work. Now we know that there is another alternative system which behaves very similarly. We already have a mathematical framework to describe that system. We will borrow it. And we will try to apply it to this one, to our states, to our silver atoms. Okay, that is after the break. Now, any questions?